Hello everyone, this is the first video of lecture 6, Duality Theory. With every linear programming problem, there is associated another linear programming problem and we call it dual. So for every primal problem, there is a dual problem. And there is a relationship between the primal and its dual, both on mathematical and economic level. Let's have an example. This is the example of slide 3. Consider a company manufactures two types of product A and B. There are three resources. So we have product A, product B. There are also three resources for producing A and B. Resource 1 is labor, resource 2 is material, and resource 3 is storage space. Availability and requirements of these resources for product A and B are as follows. For each unit production of each unit of A, we need 10 units of resource 1, 6 units of resource 2, and 4 units of resource 3. For each unit of B, we need 2 units of resource 1, 7 units of resource 2, and 2 units of resource 3. After production of A and B, the profit you can make by selling A or B is $20 for A, $15 for B. There are some limitations for resources. They are not infinite. So the availability of resources are as this: 40 units for resource 1, 54 units of resource 2, and 20 units of resource 3. Let's formulate this problem as our primal problem. Then we can talk about its dual. If you want to formulate the primal problem, we have two decision variables here, A and B, or x1 and x2. x1 represents the amount of production A, x2 represents amount of production B. The objective function is maximization of the profit, 20x1 plus 15x2, subject to a set of constraints. The constraints is the availability limit of resources. So the resource 1 used for production of A and B should be less than or equal to its limit, which is 40. We need 10 units of resource 1 to produce 1 unit of A and 2 units of resource 1 to produce 1 unit of B. So the left hand side would be 10x1 plus 2x2. Similarly for resource 2 and resource 3, we have three constraints. The amount of production A and B cannot be negative values, cannot be negative numbers, so we have non-negativity constraints as well. This is our primal problem. Let's talk about the dual problem. Suppose that another company is considering leasing the entire production facility. So they must decide on the minimum rental price of each of these resources. What is the price of this resource? If you want to rent the resources, rent the whole facility for your own production. This decision problem can also be formulated as a linear programming problem, and we call it dual. So let's talk about its dual. We have three resources and we want to make decision or decide about their price, their unit price. So our decision variables for dual problem will be y1, y2, and y3. Each y is for one resource. So for example, y1 is the unit price of resource 1. Similarly, unit price of resource 2, unit price of resource 3. There are 40 man hours or 40 units of resource 1, 54 pounds of raw materials, and 20 square yards of storage space available. Thus, the total price of all the available resources may be expressed as this formula. The price of the price for each unit of resource 1 multiplied by the availability of resource 1 is the total cost of resource 1, or total price of resource 1, total price of resource 2, total price of resource 3. We want to minimize this. If you want to rent the resources, if you want to lease them, you want to pay less. So it's minimization of this formula. This is our objective function of the dual problem. Let's talk about its constraints. The condition that the company will earn at least, the original company will earn at least as much income as when it operates the production facility itself. Since the market value, the selling price for product A is $20, so the company should earn at least $20 by renting out resource 1, resource 2, and resource 3. We need 10 units of resource 1 for 1 unit of product A. So 10y1 plus, we need 6 units of resource 2 multiplied by y2 plus 4y3 should be at least $20. So the price they can earn from each unit of resource 1 multiplied by 10 gives you the value of resource 1 for producing 1 unit of product A, the value of resource 2, the value of resource 3. So the company will rent their resources at least and at these prices y1, y2, y3, in condition that the price of those the total price of those resources should be at least $20, because with 10 units of resource 1, 6 units of resource 2, and 4 units of resource 3, they can make at least $20. Similarly, we have another constraint for product B. So they want to make at least $15 by renting out their resources. Definitely y1 and y2 should be greater than or equal to 0, because the price cannot be negative. This is the dual problem. This is the primal, this is the associated problem related to this one, it's dual. The optimal solution of this primal is $130. The optimal solution of the dual is also $130. The optimal solutions of both problems are exactly the same. Let's see how we can formulate the dual from the primal. If primal is maximum, the dual will be minimization, and vice versa. So if the primal is minimum, the dual is maximum. Constraints would be variables in the dual, and vice versa. For a maximization problem, we have natural constraints, natural direction for constraints as less than or equal to. For minimization problem, natural direction of constraints is greater than or equal to. Have this in mind. Natural constraints, if you have a natural constraints for primal, then you are gonna have greater than or equal to variables in dual. If you have a non-natural constraint in primal, then you will have a less than or equal to variable in dual. If you have equality constraint, then in dual you will have free variable. So for each constraint you will have a variable. Look at the direction of your constraints in the primal to find out what kind of variable you have in the dual. That's it. So let's solve an example. Example 1 in slide 10. It's maximization of x1 plus x2, x1 plus 2x2 less than or equal to 4, 3x1 plus 2x2 less than or equal to 6, x1 and x2 are greater than or equal to 0. We have two variables here, so in the dual we will have two constraints. We have two constraints here. In the dual we will have two variables. It's maximization in the primal, so it will be minimization in the dual. The right hand side of the primal problem will be the objective function coefficients of the dual problem. We have y1 for constraint 1, y2 for constraint 2. So two variables, y1 and y2. The right hand side of the primal problem are objective function coefficients of the dual problem. What about the constraints? You need to have the transpose matrix of these constraints coefficients. So for y1 coefficients, you use the first constraints coefficients in the primal. 1, 2. Whatever you have here in first constraints will be first column. Second constraints are coefficients of y2. 3, 2. We have greater than or equal to 0 variables, non-negative variables. So we will have natural constraints here. Natural constraints for minimization are greater than or equal to. Right hand side of the dual problem are from coefficients of the objective function. When you want to figure out what kind of variable you have in dual problem, you need to look at the direction of constraints in the primal problem. The first one is less than or equal to. It's natural for maximization problem, so we are going to have a non-negative variable. The second one, related to y2, is also natural for maximization problem. Again, we are going to have a non-negative variable. And this is your dual. Example 2 in slide 12. We have a minimization problem y1, 2y2, 3y3 subject to y1 minus 3y2 equals to 5. 2y1 minus y2, 3y3 greater than or equal to 6, y3 less than or equal to 4, y1 is greater than or equal to 0, y2 less than or equal to 0, and y3 is free. There is no limitations on the value of y3. It can be negative, positive, or 0. So we call it free variable. As you see, I try to have all of them in one column, y1 in the first column, y2 in the second column, y3 in the third column, to avoid confusion. It's a minimization problem, so its dual will be a maximization problem. How many variables I'm going to have in the dual problem? Since I have three constraints here, I will have three variables here. What are they? x1, x2, and x3. What are the coefficients of objective function in the dual problem? They are right hand side of the primal problem. It is 5, 6, and 4. Since we have three variables here, I'm going to have three constraints here. The coefficient of the first constraint will be the coefficients of the first column here. So I will have 1x1, 2x2, 0x3. There is nothing here. For the second constraint, left hand side of the second constraint, negative 3x1, negative 1x2, nothing for x3. The third constraint, 0x1, 3x2, and then 1x3. The right hand side will be the objective function coefficients of the primal problem, 1, 2, and 3. Let's talk about the direction of these constraints. The first variable associated with the first constraint in dual here is non-negative variable. So I'm going to have a natural constraint for maximization problem, its maximization, less than or equal to. The second variable is less than or equal to 0. It's a negative variable. So I'm going to have a non-natural constraint for maximization problem. Non-natural for maximization is greater than or equal to. The third variable is free. There is no limitation on this third variable. So I'm going to have equality constraint for the third one. What about limitation on variables here, x1, x2, and x3? Look at the first constraint here, because the first constraint is associated in the to the first variable in the dual. It's equality constraint, so I'm going to have x1 as a free variable. The second constraint is a natural constraint for minimization, greater than or equal to for minimization. So I'm going to have a non-negative variable here. The third constraint is non-natural for minimization. So this constraint, this variable would be a negative one. And this is your solution, the dual and the primal. Let's solve another example. Exercise in slide 14. The primal is maximization of x1 plus 2x2 plus x3 subject to 2x1 minus 3x2 plus x3 less than or equal to 6, 5x1 plus x2 plus 4x3 greater than or equal to 1, x1 and x2 are greater than or equal to 0, x3 less than or equal to 0. Let me write down the dual of this problem here. It's maximization, so I'm going to have a minimization problem. We have two constraints in the primal. I'm going to have two variables in the dual, so y1 and y2. The coefficients of objective function in dual are right hand side of the primal problem, 6 and 1. The coefficients of the first constraints is the first column, so 2y1 plus 5y2. Second constraint, negative 3y1, 1y2. Third constraint, I will have three constraints here because we have three variables in the primal. Third constraint coefficients are 1 and 4, y1 plus 4y2. Right hand side of the constraints here are the objective function coefficients, 1, 2, 1. x1 and x2 are greater than or equal to 0, so the first and second constraints in the dual will be natural for minimization. They are greater than or equal to. The third variable here is less than or equal to 0, so I'm going to have a non-natural constraint for minimization, which is less than or equal to 1. What about the limitation on y1 and y2? You need to look at the direction of the in the constraints of the primal problem. Less than or equal to is natural for maximization problems, so it's a non-negative variable. Greater than or equal to is non-natural for maximization problems, so I'm going to have y2 less than or equal to 0.